At the turn of the 20th century, physicists knew that atoms were the basic building blocks of matter, and that they contained negatively charged electrons and positive mass. But the exact arrangement of those internal charges was a total mystery. In 1911, Ernest Rutherford designed an experiment to map the inside of the atom. His method was direct. He fired a beam of dense, positively charged alpha particles at a target of incredibly thin gold foil, expecting them to punch right through the uniform atomic structure. As a positively charged alpha particle approaches the heavy gold nucleus, it experiences electrostatic repulsion. While most particles passed straight through the foil, a tiny fraction deflected sharply, and a few violently ricocheted straight back. These extreme deflections proved that the atom is overwhelmingly empty space, with all of its positive charge concentrated in a microscopic, ultra-dense core. This meant the negatively charged electrons had to be orbiting this distant nucleus, much like planets circling a sun. Treating the atom like a tiny solar system created an immediate theoretical crisis. Under the strict rules of classical electrodynamics, an electron moving in a circular path is constantly changing direction, which means it is constantly accelerating. Classical physics mandates that any accelerating electrical charge must continuously radiate electromagnetic energy into its surroundings. As that orbital energy bleeds away, the electron's velocity drops. The electrostatic pull of the positive nucleus takes over, dragging the electron into a tighter and tighter orbit until it crashes into the core. Calculations showed this collapse should happen in a fraction of a nanosecond, yet the physical universe exists. The atoms in your body and the gold foil in Rutherford's lab are entirely stable. The existence of solid matter directly contradicted the known laws of physics. To explain how an atom survives its own internal forces, the mechanical rules governing the microscopic world required a complete revision. In 1913, Niels Bohr proposed a theoretical intervention to bypass this structural failure. He started by simply declaring that the classical rules didn't apply inside the atom. He stated that electrons inhabit specific, stationary orbits, where they revolve without losing any energy. To define where these allowed orbits sit, Bohr quantized the electron's angular momentum. He introduced this equation, requiring that momentum scales by a variable n, which must be an integer. An electron can exist at n equals 1 or 2, but never 1.5. This integer math effectively locked the orbits into discrete tracks. But Bohr had no physical justification for this rule. It was an ad hoc fix, inserted simply because it yielded the correct answers. He successfully engineered a mathematical framework that mandated atomic stability, while leaving the actual physical mechanism of these strange, non-radiating tracks completely unexplained. Locking electrons into these specific spaced-out tracks meant their energy was also locked into fixed intervals. This chart visualizes these discrete energy states. Using the equation negative 13.6 over n squared electron volts, we see the ground state at n equals 1. As the orbital level increases to n equals 2 and 3, energy values step up in specific quantifiable increments. An electron can jump between these rungs. If it absorbs energy, it moves to higher orbit. But when it transitions back downward from an excited state to a lower level, it must shed that exact energy difference. It releases this energy by ejecting a photon of light, perfectly matching the difference between the initial and final energy states. Because the energy gaps are fixed, the ejected photons always have specific, unvarying frequencies. When we observe the light emitted by heated hydrogen gas, it doesn't produce a continuous rainbow. We see distinct, bright lines of specific colors. This spectral fingerprint serves as the physical proof that Bohr's quantized energy levels, despite lacking a mechanical explanation, accurately describe the architecture of the atom. Bohr's mathematical framework worked flawlessly to predict these light frequencies, yet the underlying mystery remained. What physical property forced the electron to obey integer math? In 1924, Louis de Broglie looked to the dual nature of light to solve this mystery. If light, long considered a wave, could behave as a discrete particle or photon, de Broglie hypothesized that this symmetry must work in reverse. He proposed that the electron, a known particle, actually possesses the geometric properties of a wave. This diagram illustrates his concept. De Broglie formalized this duality with a single equation. A particle's wavelength is equal to Planck's constant divided by its mass times velocity. By reimagining the electron as a continuous wave rippling through space, the problem of orbital stability shifted fundamentally. It was no longer a problem of classical particle mechanics, but one of wave geometry. When a wave travels in a closed circular loop, it faces a strict geometric constraint. If the wavelength doesn't match the orbit's circumference, it destructively interferes. To survive, the electron forms a standing wave, where circumference equals an integer number of wavelengths. Substituting de Broglie's equation and rearranging yields mass times velocity times radius equals n times h over 2 pi. The term on the left is angular momentum. The result perfectly mirrors Bohr's second postulate. His ad hoc mathematical patch wasn't arbitrary. It was the inevitable result of an electron existing as a standing wave around a nucleus. This wave-particle derivation provided exact predictive power for a single electron system like hydrogen. This graphic details the final accounting. The Bohr-de Broglie framework successfully explained quantized orbits and the origin of spectral lines, but the limitations column shows where the framework hits a rigid wall. When applied to helium or any highlights the attraction between one electron and the nucleus, it fails to compute the repulsive forces between multiple electrons sharing the same space. It also falls short observationally. It cannot explain why certain spectral lines burn intensely bright while others are dim, nor can it account for the microscopic splitting of individual colors into fine structure lines. The standing wave concept prevented the classical collapse of the atom. But to decode the mechanics of the entire periodic table, physicists needed to abandon the idea of flat, two-dimensional circular tracks. The next step required discarding the concept of a determined physical orbit entirely. Instead of precise tracks, the modern model describes electron positions through complex Schrödinger equations, generating three-dimensional probability zones. The strict geometry of planetary rings dissolves into hazy clouds of chance, spherical s orbitals and dumbbell-shaped p orbitals, showing where an electron is likely to be, rather than where it exactly is. This journey reveals that the stability of all matter relies on a trade-off. To accurately model the atom, physics had to sacrifice the intuitive certainty of particle paths for the exact geometry of three-dimensional standing waves.